Hello everyone, this is Sanath Chilakala. As you guys know, mainframes has been around in multiple industries over the last couple of decades. They've been supporting with very robustness, scalable, and have been supporting operations like financial transactions, insurance processing, healthcare transactions, and all of that. But however, at some point, we have to modernize these mainframe applications. And the best way possible is right now to use an AI-powered approach and basically see how AI is basically enhancing the reliability in this legacy system transformation. As enterprises continue to rely on mainframes for mission critical applications, AI basically offers groundbreaking approaches to modernize these systems while maintaining operational stability. Today, we're going to talk about what are the different technologies and tools AI basically offers to enable this transformation journey and focus primarily on the reliability engineering principles as we do that. As you can see that there are some key features from AI that are used as part of this transformation journey, which is automated code analysis, intelligence testing, predictive monitoring, and showcasing how these site reliability engineers teams harness these capabilities to ensure that this transition is seamlessly done, even in the most critical environments possible. Now, let's talk about some of the challenges that we encounter during this modernization process. One is the legacy dependencies. There's a lot of logic and code built over the years that with limited documentation that we need to basically start identifying and tracking down. There's very complex interdependencies between systems built over decades. The next would be the knowledge gap. Most of these mainframe systems are built based on COBOL. The COBOL is a very obsolete language today that we don't have the people with the right skills to manage and maintain the system or even understand what the code in the current system is. The next would be the operational risk. Since, as we mentioned earlier, that these mainframe systems are used in very high transactional operation systems, the risk and stakes are very high when they're during this transaction and there is downtime required. The last would be performance. So when during modernization, the expectations are usually very high that the performance should be subpar and to ensure that it outperforms the old legacy transaction system. But there are factors like scalability that needs to be taken into consideration during this transition. Next would be how AI is basically enabling us to determine what kind of resources and scaling that are required for this specific migration. As you can see on the graph, that we have three different types of tracking. One is a traditional tracking method. That means traditionally, if you don't use AI, you come up with a prediction of this is how it's supposed to be how it's supposed to be scaled as part of this modernization. Second, then in the green, you see that's an AI-driven approach wherein it understands the existing system, tries to identify the dependencies, and gives you predictability of how much resources need to be allocated to make this happen. Then when you start to compare with the actual usage, you see that the actual usage correlates highly with how the AI is predicted. By leveraging these AI different techniques, you can reach accuracy levels of 95%, and in very mature implementations, even the best of the best traditional mature implementation, we achieve only to 60 to 70% accuracy. Next, we talk about basically how natural language processing is playing a very key role in trying to basically transcript the existing documentation. So what NLP does is, what AI brings into the picture is it basically can start to document any kind of manuals, documentation available, and starts to learn and train itself and trying to provide you actionable insights to determine how reliability and scalability needs to come into picture. Then, at the same time, as you mentioned earlier, by reading through this documentation, it tries to identify the different dependencies and starts to create that semantic analysis and mapping around the different components of this implementation. And the last would be knowledge graphing. The knowledge graphing is basically trying to create a map around the different sources of information identified as part of the documentation. NLP with AI basically provides us the capability to parse through this unstructured documentation and provide you very valuable insights, which are very key for any kind of migration activity. Next, let's take a case study, an active case study, which is implemented out there in the financial services industry. So the project scope, as you can see, that it is a 30-year-old legacy core banking system with comprising of around 5.2 million lines of complex COBOL code and 400 mission critical dependent applications over the decade. And then very strict zero downtime requirement because this is a financial services environment. How AI basically enabled this migration? First, it was able to do comprehensive automated dependency mappings, as we mentioned earlier, that using NLP, trying to understand documentation, trying to create those semantic mappings, it was able to achieve that. Next would be to use AI to generate advanced predictive incident prevention. That means you have to understand how to leverage AI to understand what kind of issues might foresee while doing a migration activity. And AI can provide you better tools and enablement to catch this ahead of time and try to save the time for debugging and trying to resolve it ahead of time itself. The next would be the real-time performance monitoring with alerting. So while doing the migration transition of piece by piece or sections of each of the system, this real-time monitoring basically enabled us to basically start to see if there is any dip in performance or any spikes that we're noticing that we're not aware of, and also generate alerts to enable users to understand where it is going wrong. And then the last would be, this is the most important critical piece, while doing the migration from the legacy to a modern system, the key is testing. So how manual testing over the years has always been skew in entire project planning or migration planning. AI basically enables us to do automated intelligent test generation, which will automatically do the testing for us while we transition the code from one system to another. So the outcome of it, these are the outcomes that we have encountered. We have basically reduced 72% in critical production incidents. We have cut short the migration timeline by 14 months. And in overall cost savings, we have saved around $4.3 million and 99.998% system uptime maintained throughout this implementation or this migration. Next, let's talk about, as I mentioned earlier, the criticality of this testing is very key during any kind of a migration initiative. There are 4 different capabilities that AI offers during this creating a testing framework. One, it provides you a test generation capability. It provides a comprehensive test scenarios based off the documentation, the migration, the user stories, the product documentation, all of that. Then the automated execution. Once the code is ready, automatically the AI basically provides us the tools to pick up the code, run through the testing scenarios and tell us whether it is working or not, or it also tells you which part of the code is basically causing the issues as well. Then, based off the results that we have encountered over a period of testing, it also enables us to basically create pattern recognitions in all of the testing outcomes. It will enable us to predict in future code migrations how we can leverage all of that predictability to write better code and to do better migration activities. And then the last piece is the test refinement. So as we start to train the model to understand what the different test scenarios could be, and when we start to implement these product scenarios via code, it starts to self-improve itself and starts to write better testing scenarios and provides a better testing coverages. Next, this is the implementation framework. How do we implement AI? First thing is the assessment phase. During any kind of migration activity, the assessment phase is very key because that is where you catalog all existing systems, identify modernization candidates, and establish reliability baselines using automated discovery tools. Next, we start with the pilot. We basically take a simple MVP and then start to migrate that or modernize that based off using AI-driven reliability improvements and scalable approaches and refining approaches to do that implementation. Once the pilot is successful, then is basically the implementing AI at a larger scale. Then we leverage AI and tooling within existing SRE practices, focusing on code analysis, predictive monitoring, and automated testing capabilities. The last would be scaled deployments. Now that we have implemented a pilot, you have now implemented the integration capabilities. Now we leverage AI to determine how much scaling is required for this to successfully work the way it is supposed to work, or you perform even better. So we extend proven approaches across the enterprise, maintaining continuous learning loops to provide modernization outcomes. Then, what are some of the common challenges and mitigation strategies that we need to consider during this migration? One, data quality issues. Primarily, when we move from one system to another system, we have to take into account but that each of the system acts in a different way. It ingests data in a different way. It reads data in a different way. So we need to basically implement very data cleansing pipelines and verification algorithms to ensure AI systems receive reliable inputs. And then we'll have to establish data quality scoring mechanisms and trigger human review for edge cases. Then, technical debt. Ideally, there's a lot of technical debt which is involved during any kind of a migration activity. We basically need to use AI to quantify that and categorize the technical debt, creating prioritization remediation roadmaps. Then we'll have to make sure that we implement automated refactoring tools to systematically address high impact issues first. So the prioritizations and everything are very key to any kind of technical debt. So whatever product backlog we have, technical backlog, we have to ensure that we prioritize it and we start to roll it out according to that itself. And then comes the skill gaps. So as I mentioned earlier, the primary problem with legacy mainframe systems is to find people who have that COBOL understanding and knowledge. So we need to basically start to bridge the limited set of mainframe veterans that we can identify and bridge them with AI specialists to basically do a proper knowledge transfer and then ensure that AI is properly educated among these mainframe veterans to understand and then bridge the product gap and bridge the technology gap. Now, let's talk about some future directions, like how quantum computing applications is a game changer in this specific migration activity. First, it would be around complex optimization problems. Quantum algorithms will dramatically accelerate optimization challenges in resource allocation and performance during mainframe transition, solving in minutes what currently takes days. Quantum computing basically gives you the capability to process problems or solve problems in a very fast method. I'm talking about microseconds, not even seconds. It is that fast. We're still not there today, but in the future day, once we get into quantum computing, it solves many other cases, not just pertaining to modernization, but it solves many other scenarios and questions as well, including space travel, including automated language learning. There's a lot of areas that quantum computing can help. Then, next would be how the enhanced security modeling of what quantum computing offers. Quantum-resistant cryptographic systems will safeguard sensitive data during migration, while quantum simulation will identify potential security vulnerabilities possible to detect with classic computing. What this means is it provides you the different tools and encryptions possible while transitioning data from one system to another system. We have a traditional encryption methods that we follow today, but this cryptographic encryption is taking this to the next level. It will proactively identify all system vulnerabilities, security vulnerabilities, and try to identify what remediations can be in place and provide better encryption and cryptographic capabilities to safeguard it. The next capability is system behavior prediction. Quantum machine learning models will achieve unprecedented accuracy in predicted system behavior under load, enabling perfect fit capacity planning during critical migration phases. What this means is basically it allows you to provide you high levels of accuracy while predicting a certain scenario. Whether it is system behaviors, whether it is capacity planning, whatever it might be, in every migration phase, it can give you unprecedented accuracies when trying to implement predictability in that scenario. So early research basically now suggests that quantum approaches could possibly reduce complex migration timelines with 30 to 40% while improving reliability outcomes. That is a big number. Then, practical guidance for SRE teams. So for site reliability engineering teams, some of the things that we need to consider why AI is a major player in any kind of an SRE environment is, one, it basically reduces the incidents by 89%. It is a proven fact done and implemented and validated across multiple implementations. Average reduction in critical incidents during modernization when using AI-driven reliability tools has reduced by 89% compared to a traditional approach. Then, the ROI is very key. The money plays a major factor, or any kind of an ROI plays a major factor during an investment. So any kind of a mainframe modernization project has to be backed with an investment. So with AI being a major part of that migration activity, it is proven that, or theoretically we have identified that the ROI is basically generated 3.7 times what it was supposed to usually provide in a traditional migration activity. Then, using AI assistance, we can save the time and planning efforts required as part of the analysis. So during planning phases, analysis phases, there were proven cases, the studies say that we were able to achieve 65% of time savings during analysis and planning phases. So overall, I want to make sure this is how I want to conclude that AI plays a very major role in how the reliability, scalability plays a major factor during any kind of a complex migration activity involved. So all of my friends who are thinking about migrating legacy system, please ensure that AI is implemented as part of that, and all of those and use my inputs to basically drive your leadership towards understanding what are the different benefits AI can offer during any kind of migration activity. Thank you so much for everyone's time. Have a lovely day. Thank you. Bye.